Hi, welcome to a quick lesson on impulse and momentum. Just a quick reminder, actually solving these problems is really just the first step toward understanding. We need to be able to explain what the big ideas are, be able to apply them in new situations, and be able to teach them to somebody else really before we could say that we have deep understanding. And so just working these problems is the first step on the journey. Okay, so with that in mind, what is the big idea here? Well, it's that we can deal with impulse, the change in motion caused by a force times time, and it is equal to change in momentum. And so we're going to use that here to solve one of the problems taken from the workbook. So here's a pretty typical situation that we could use to consider impulse. We have a kid in a bumper car who collides with the side of the bumper car arena or whatever, and the side pushes with about 4,000 newtons on the car, and it applies that for 0.2 seconds. So first question, what is the impulse? All right, so working on that one is kind of a straightforward one. Our impulse is the change in momentum. Now, quick note, in some textbooks, this gets its own variable, J. So some college textbooks would say J equals and ask you to solve for that impulse. But it's asking for the same thing. It is the impulse, it is the change in momentum. We know here that the force is 4,000 newtons, and we want to pay attention to what the direction is. So let's just do a little setup for ourselves here. Let's say the car is going along, runs into the side. The wall would push to the right. So the 4,000 newtons that brings this car to a stop is pushing to the right. The time is 0.2 seconds. And so if impulse is our unknown, we can just apply our basic formula here and say force times time, 4,000 newtons, times our 0.2 seconds, and that gets me an impulse of 800 newton seconds to the right. The direction of the impulse is the same direction as that of the force. Quick moment for units here. Momentum itself is mass times velocity. Mass is in kilograms, velocity is in meters per second. So why do we have kilogram meters per second here and newton seconds for change in momentum? Well, it turns out these are the same thing. If you plug in for newtons, kilogram meters per second squared, do the math on it, it will turn into kilogram meters per second. So newton seconds, kilogram meters per second, same thing. All right, let's look at the second part of the problem. Now we're being asked to figure out the final velocity of the car after this collision with the wall. It didn't say that the car comes to a stop. It might, or it might bounce backwards. Obviously, in this case, it wouldn't continue to move forward. It's not going to move through the wall. And we want to be aware of all these things as we're solving this problem. Want to acknowledge really quick that with these givens, the 2.8 meters per second and the mass, and with the force and other stuff involved, we could solve this using methods that we have previously learned. But I want you to look at this from the perspective of solving it using momentum and see how impulse and momentum fit in here. So V final is our unknown. Our V original is 2.8 meters per second, and in the setup we showed before that we sketched, we had the car moving to the left, and we want to pay attention to that. Its V original is to the left in this drawing. And the force from the wall, on the other hand, we knew was to the right. The impulse, the change in momentum that we calculated, was to the right, 800 newton seconds to the right. Okay, left, right, left, right. One of these needs to be a negative to make this work out mathematically. That's why we're paying attention to the direction. So what I'm going to do is I'm going to call this a negative 800. It is pushing backwards on the car. Now, honestly, it doesn't matter whether I make this negative or this negative, the velocity or the delta p. It's just that one of our directions needs to be designated as negative. We need to include these negatives when we have opposites. And you'll see that that comes into play when we do the calculations in just a minute. Okay, so we know this much. and we know that the mass of the kid and the car together is 200 kilograms. Now you might be looking at this and going, this doesn't match our part about force and time and impulse. But we're reminding ourselves that impulse is change in momentum. And if momentum is mass times velocity, then what I'm looking for is final momentum minus original momentum, and I want to look at what has changed. Has the mass changed? Well, the kid in the car, they have the same mass, and I'll tell you up front, most problems, the mass of a single object will not change. If we start changing the mass, we're very quickly, literally, getting into rocket science. In this case, the velocity has changed. So the changes between the momentum in the beginning and the end is going to be a matter of v final and v original. And you can see when we look at it from that perspective, suddenly it should become a lot more clear. Oh, there's the unknown that I was looking for. So my change in momentum equals mv final minus mv original. Let's solve to get our v final alone. If I do that, I get my impulse plus mv original divided by mass. And if I go ahead and put in the numbers, this is where getting that negative in there for the 800 is important. Negative 800 Newton seconds plus our 200 kilograms times our v original of 2.8 meters per second. And there's that relationship again, Newton seconds and kilogram meters per second, they're the same thing. And we had to divide that by our mass, our 200 kilograms. So when I have kilogram meters per second and I divide out kilograms, what am I left with? I am left with meters per second. If I type all this into my calculator, pay attention to making sure to solve the top first and then divide by 200, I get negative 1.2 meters per second. What's the negative mean? The negative means that this is opposite from the original direction. So not surprisingly, the car is bouncing backwards. It hits the wall and bounces back. So we can get information about this and look at it from the perspective of a changing momentum and end up actually solving this problem in a very quick fashion. So this can be a very powerful tool for analyzing situations, and I encourage you to practice with it. See you next time.